Hello, everyone, and welcome to today's webinar, the evaluation of elevated temperature performance of materials. My name is Mike Moran. I'm the VP of Business Development and Engineering at the Gun Company, and I will be your host for today's session. First, I would like to thank everyone for taking time out of your busy schedule to attend today's webinar. Before we begin, I want to cover some basic housekeeping tips to maximize the value of your webinar. To ensure the best connection possible, please close out any programs or apps that may be eating up a lot of data in the background. To free up your bandwidth space, if you experience any technical issues, please call the help desk support line at the number provided in the chat box. You can join the audio using your computer. However, if you would prefer to join over the phone, just select telephone in the audio pane and the dial-in information will be displayed. This will also help clear up some bandwidth. Your audio settings will be set to listening only for the presentation portion of the webinar. You will have the opportunity to submit text questions to today's presenter by typing your questions into questions pane of the control panel. You may send your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. Any unanswered questions will be followed up via email following the presentation. If you would rather ask a question directly rather than type it, raise your hand and we can unmute you. Today's webinar will be recorded and available on demand, and a link will be sent out to all attendees within the next 48 hours. So, without further ado, I will like to introduce Solomon Chiang. Solomon Chiang is Director of R&D for the Gun Company, in St. Louis since 2021. He was previously Director of Engineering from 2010 to 2020. He joined TGC in 2008 through the acquisition of Weidman Industries in Canada. And Solomon joined Weidman Canada in 1997 as engineering manager. Solomon graduated from McMaster University with a PhD degree in analytical chemistry. He's active with standards organizations and currently chairs the NEMA Technical Committee for 6IM Insulation Material, the 6IM Insulation Material section, and serves as secretary to IEC TC 15, the solid electrical insulating materials. Dr. Chiang is also a voting member of IEC Transformer Committee and serves on the standard technical panels for UL 224 and UL 1558. So, without further ado, Dr. Chiang, over to you.
Good morning, good afternoon, and good evening for those of us joining from Europe. And today we are going to talk about RTI, TI, as well as thermal classes for insulating material and insulating system. The purpose of today's webinar is to have a better understanding on the meaning, significance, and different methods to determine RTI of polymers and composites. And we want to be able to understand the difference between RTI or TI thermal index of a single material and the temperature or thermal class of an electrical insulation system using such materials. And lastly, we would like to talk about discuss about the new NEMA IM60001 standard, used to be called LI6. The new standard would improve our understanding, hopefully, on these subjects. For those of us who work with UL, who have a yellow card, and who have to review yellow card for our material or product application, we understand that on the yellow card, on the right-hand column, it says RTI. Okay, what does that mean? The RTI is a reflection of the long-term thermal endurance of the material. Okay, you can obtain RTI two ways. If you don't want to spend the money, then UL will give you generic RTI based on the chemistry of the material. And the generic RTI that UL gives out is very conservative, sometimes even useless. If you look at the example below, polypropylene has a generic RTI of 65 degrees C. That's just a little bit more than warm water. And we know that engineer grade polypropylene can do a lot better than that. Even very high-end material like PI, polyimide, we know it's a 200 and 220 degrees C material. The generic RTI is only 130. So obviously, for a manufacturer, we do not like to use UL generic RTI. So if we want to test our RTI, then that's what UL call long-term properties. It involves aging of the insulating materials. And scientific studies have proven that thermal degradation is a dominant aging factor over time in the majority of applications. And the degradation of material properties can be mechanical, can be electrical, can be both. Over time is non-linear at elevated temperatures. What it means is that at the beginning, at certain elevated temperature, the degradation is slow, and then it accelerates, not in a linear manner. And with UL, long-term thermal aging for materials covered under UL 746B, mechanical is tensile, and if the material is thick enough, impact also. Electrical is always dielectric strength. The thermal degradation follows the Arrhenius equation of activation energy. What it means is that the higher the aging temperature, the faster is the degradation, but in the non-linear manner. Okay, I keep talking about degradation. So degradation of the material properties is what we want to measure. But how? Well, what it is that we use the Arrhenius equation, and this is what the Arrhenius equation looks like. The K is a specific reaction rate, and it is proportionate in an exponential manner to the reciprocal of the absolute temperature, 1 over T. And in order for us to measure the degradation, we have to define an endpoint, the point where we say the material has degraded. And UL use 50% of loss of property as compared to the original sample or unaged sample. And one thing I like to point out here is that the 50% is more historical than safety related. If you, under UL 746B, section 11.2, it kind of assures the user that if the material degraded to half of its initial property, it does not mean the material is unsafe to use or the appliance that use the material is not safe. It is just that the 50% is used historically for the RTI and TI determination, and all the data are based on 50%. As you can see later, RTI means relative thermal index. It is comparison of one to the other of a known material. So we need to compare apple to apple, and that's why we use 50%. And another reason why we use 50% is to provide a certain amount of safety, knowing that the material can degrade up to 50% and it still does not compromise safety. With UL, safety is always number one. Material properties is after safety. Now, we talk about endpoint, so we know what the endpoint is, half of the original property. So how do we get to the half of the original property with thermal aging? Well, I mentioned UL 46B. That's been around since the 1970s. And in the last 30 years, the IEC 60216 series is the equivalent of UL used in Europe. And the two methods are very similar. And I'll talk about a little bit of difference between the two methods later. Essentially, we are talking about 50%, so we have to know our starting point. So we measure initial property. We do the tensile test, we do the impact test, and we do the bioelectric test, and then we start aging. So usually RTI means relative. So you pick a control or reference with a known RTI and age it side by side with the candidate at different aging temperatures. That's what we call RTI. If you choose not to use a reference, that's fine. But what you get is a TI without relative for opposite reason, it's by itself. What we do is that we have, for each aging temperature, we test it at different time intervals. UL called cycles, IEC called cycles also. And we determine the percentage of property retention. And the higher is the aging temperature, the shorter will be the test duration. That means the cycle will need to be a lot shorter. It can be as short as 2 days or 1 week. At lower temperature, the cycle could be about, say, 3 weeks, a month. What we do is that at each temperature, we plot the curve of the hour to 50% degradation or endpoint. And then, say for example, we test at 4 temperature. Each temperature gives us the hour to the endpoint. Then we plot those hours against temperature, and then to determine the correlation hour. And what is correlation hour? So universally, pretty much UL, IEC, NEMA consider 20,000 hours as the correlation hours. That means 20,000 hours is a good enough time for material to reach the end of life at its RTI or TI temperature. So you may argue that 20,000 hours is only 833 days, just 2.25 years. That's not too long, 2.3 years. But it is accepted because your material would not be continuously exposed to the RTI or the temperature index on a continuous basis. I mean, obviously, if it has hot and cold cycle, your appliance is not always running super hot all the time. So 20,000 hours is considered as adequate for correlation hour. So that is for TI. That means you are doing the testing of your material by itself. For RTI, the correlation hour can be 10,000, can be 20, can be 30,000 hours. What it is that correlation hour is the hour where the adherence plot of the reference intercept is known RTI or TI temperature. That is your correlation hour. I will have graphical example to show how it's done. UL also has a provision. UL will give you an RTI if you choose not to have a reference, but UL will be more conservative. UL will require 60,000 hours. That's almost like 7 years. And obviously, if you want an RTI, it would be preferable to do the RTI with a reference, because 60,000 hours would be very, very hard to get a good RTI number. Okay. So this is the traditional method for RTI or TI determination using 4 aging temperatures. From left to right, 190, 170, 149, 130 degrees C. So those are the each aging temperature. At each aging temperature, you have between 8 to 10 cycles. So at each cycle, you measure the percentage of property retention. And UL require a minimum of 5 samples to be tested at each cycle for statistical reason. So you cannot just do one. And then you draw a horizontal line at 50%, and then drop it down to the x-axis. That's your aging time in hour. So as you can see, the lower the temperature, the longer would be your aging time in hour. For example, in these cases, at 130 C, it takes about 7,000 hours to reach half property or 50% degradation. So from all this cycle, you end up with 4 data points at 190, 171, 140, and 130. And then you plot it, and then you extrapolate to 20,000 hours. So that's like, that would be your TI. That's doing it by itself, doing the material. If you have a reference, then you age the reference side by side with your candidate. You are called a candidate. That's the one you want to determine the RTI. And then you take the TI or RTI of your reference, and whatever temperature it is, say 200. Then from 200, you draw a vertical line all the way up until it intercept the Ahearn's plot of your reference. And then from that point onward, you draw a horizontal line across until it intercepts the Ahearn's plot of your candidate, and then drop it down. Say if you drop it down to the temperature scale at 180, your reference is 200, and then your candidate would be given an RTI of 180. So this is what they call a graphical method. And obviously, you need, because this is the lot versus 1/over reciprocal graphical paper, it's not easy to use. And in the old days, you pretty much need a very large graph paper with good resolution to get an accurate number. However, both UL 746B and IEC give you in detail how you can do it mathematically. First one is the property degradation over time at any of the elevated temperature is a polynomial equation. I think it's a third order one. And then my analytical geometry has left me a long time ago. I'm not trying to explain this, but it works. So you can go through all the calculations, and then you can take the regression line and transpose it into a linear equation, y equal to a plus bx, and plug everything mathematically, and we solve all the equations, and then you can solve TI using 20,000 hours or correlation hour, or you can resolve the correlation hour from the known RTI and TI of the reference to get the RTI of the candidate. So that's mathematics. Okay, the mathematics is complicated. Imagine if you do it by mathematics only, without the graphic, without the graph paper, without the plot, it will be hard to understand. Nowadays, with computer software, we get the best of both worlds. It gives you the accuracy of mathematical method, but display in a user-friendly graphic so everybody understands. And also, I mentioned that with any UL test, you cannot just, at any cycle, you cannot just test 1 or 2 coupon. You have to test minimum of 5. Anytime you test 5, you get a lot of statistics. And then when you plot regression line, you get a lot more statistics, like the correlation of regression, the confidence or limit. The software will give you all those. Essentially, those are the reliability data of your RTI. If you get one, say on a yellow card, say 180 degrees C, how reliable it is. The yellow card doesn't tell you. It is all in the proprietary test data. I'll talk about it more at the end. This is just an example of the computerized method for data analysis. The material is an element material called YT510, and then it gives you the graphical plot. It shows you how that's the average and that's the variation. This is your 95% confidence limit. It gives you 227 degrees C TI because it's by itself. The regression, correlation of regression is very good, 0.9999. So you can tell the points are right on the regression line. And that means that at the lower 95% confidence limit is 226, so not that too far away from 227.4. So that's the best of the both worlds using computer software. And it also gives you another number called halving interval. It is essentially the slope of your heinous curve expressed in a linear fashion. And this halving interval is useful because just like a rule of thumb for product design margin, if you have a material that's 180 degrees C at 20,000 hours, then I say, I want to allow myself some more margin because I expect my appliance or my equipment to last a lot longer. Then you may have to drop it to 170, the operating temperature of your appliance. That means that you will double the life. On the other hand, if you want to run your appliance hotter, then you know what kind of compromise you would have on the insulation. Because for every 10 degrees, you would drop, the life will be half or double. The same thing goes for halving interval of 5. And one thing we found out is that for most insulation material, the halving interval is usually around 10, between 9 and 11. Now, I'm going to show another option for doing RTI or TI determination, and it is called proof test option. As I mentioned before, you need at least 5 replicates at each cycle. And then if you have 10 cycles, you need 50 specimens at each temperature. And we know that the more you test, the more expensive, the more time consuming it gets. So there is a proof test option which can reduce the number of specimens. What it does is that first you determine the what we call the proof properties. For example, if you want to do dielectric, and we found out that we pick up 10 samples, and based on the 10 samples, the average breakdown voltage is 4,000 volts. Then the proof voltage is 2,000 volts. And then you take 21 samples instead of 50, and then you test it and then at each cycle, you take out the sample and test it at 2,000 volts. Those fail will be assigned an M-con midway between the hour at the failed cycle and the previous cycle. And then those you pass, you just put it back into the oven and keep aging until 11 or more of them fail. Then the remaining one will be assigned the M-con hour at the at the last cycle. And then what you do is that you take the geometric mean, that will be the M-con of the at that temperature, and you do the Heinous plot just like what I demonstrated before. So that is what UL call proof test method. I bring it up because it's important when we reach the end. Well, this is as I said before, UL 46B is the most popular way of doing thermal aging, RTI and TI determination. Below are the IEC series. and essentially they are very similar. I mean, there's actually the biggest difference is probably UL. If you use UL to do the testing or UL approved lab, and the number looks closer to UL, they'll put it in your yellow card so that you don't have to use the generic number. And IEC, if you test IEC does not have a yellow card system. So if you have a reputable outside lab performing the RTI test using IEC method, then you just put it in your technical data sheet, and then you can say test as per IEC 60216-3-4. And those are the rules, because the rules are there to make sure that the results are comparable. When you compare one material to the other, you know that they are kind of test under controlled manner. There are some minor difference between IEC and UL, but it's not a big deal. So I won't go through all those. But now I'm going to talk about another method. Actually, it's used by both. It's used in UL section 22, and IEC actually create a new standard. There's 6 of IEC 60216 to talk about it. It's called fixed time method. In the example that I showed before, at the lowest temperature, UL require minimum of 5,000 hours, and so the material has to reach 50% degradation, no less than 5,000 hours. From time to time, it could be 7,000, it could be 8,000, it could be 10,000. So it's a long time to get one number. So UL come up, and both UL and IC come up with this fixed time interval. So you do it essentially 5,000, 500, 1,000, 2,000, and 5,000 hours. But instead of measuring the property or property degradation at each cycle, you just measure it at the end of the time interval. But for each time interval, you have to test at 4 different temperatures. The whole idea is that you should reach 50% property degradation between the two top temperatures, so that you can interpolate the 50% of the half-life. And what it does is that it ensures your test will be done in 5,000 hours. So in theory, it saves you some time, but in practice, you're probably not getting a lot of saving, because you have to do a lot of pre-screening to make sure that you select the temperature properly in order to satisfy those rules above. And the other one that I want to mention a little bit is that with IEC, you get a number. The number is often down to 1 decimal point. UL would not give you a decimal point RTI. Actually, UL would round it to some nice even number. For example, for most material that we are talking about, they are between 130 to 220. And usually, UL saying that if you have 135, even at 138, it will be round down to the nearest 10 degrees C. Always round down. That's UL's rule for being conservative. Now, that's the problem with rounding down number, especially when you are talking about RTI. Say we have two materials, two high temperature material. A has a TI of 217 and B has a TI of 221C. Assuming that we are in a hypothetical situation, we are using material B as a reference to determine the RTI for A. Because material B cannot be used as cannot be called 221C, it will be round down to 220. And after we've done our RTI plot, I will show that in the next slide. A would have an RTI of 215, 215, but we can report 215. It has to round down to 210. Okay, now if I flip it around, I'm using material A as a reference, so it's 210. And then if I plot it again, the RTI for the B would be 216 C, and I need to round it down to 210. So even though it has the RTI, even it has a TI of 221 degrees C initially, somehow, if I do it this way, compared to A, and using A as a reference, I'll end up with 210 degrees C. And this is the graphical representation of what I talk about. First, I use B as a reference. I get RTI of 217 for A, round it down to 210, and then because I use 210 as a reference, I have to move, see the blue line, I have to move it 10 degrees to the right. And then if I take the blue line to go all the way up and intercept on the reference, go across to the candidate, this is B at this time, it's 216 or 215, I'll round it down to 210. So that's one of the problems with the rounding of a system. I will elaborate a little bit further later. Okay, for the last 10 minutes, I'm going to talk about the insulation system. It's where essentially, if you have more than one material, insulating material, it is called an insulating system. And then in the insulating system, the thermal degradation is influenced by the chemical interaction of all the material in the system. So it's not just temperature. For if you age a material by itself, the temperature is a dominant factor. Here you have to worry about the chemical interaction of all the other material in the system. And UL 1446, which many of us are familiar with, is the gold standard. IEC has equivalent, but IEC cannot match it in popularity. Why? Because for those of us who are subscribed or who sign up for ULIQ, you can see that there are thousands of electrical insulation systems in the UL's database. So how can you compete with an organization who has thousands and thousands of historical data? Now, before I proceed to talk about how we do RTI or thermal class for a system, I would like to introduce some of the newer terminology used by UL. And the one that we have to remember is that the major or primary insulation in a system is now called EIM, electrical insulating material. The minor or secondary insulation that are not in direct contact with live part would be called NIM, non-insulating material. Don't worry. I mean, a lot of people complain about this term. They are insulating material. They are not metal. I mean, so this is really not a very good term. It's just that they are not in direct contact with the live current. So if you see NIM, don't worry. And MIM or minor insulation, this may be I think this is something that only happened recently, maybe by recently in the last 10 years. If you are substituting a minor insulation on an electrical insulation system, and if the fingerprint match of what you want to, the material you want to substitute for, you do not need to do any additional test. It can be just what we call like a no test upgrade to your UL insulation system file. If it doesn't match, you have to do a chemical compatibility test on a sealed tube test. I just want to bring it up. Now, how do we do thermal aging for EIS, or electrical insulation system? The concept is similar, but I'll talk about the difference in test terminology, in test methodology on the next slide. And again, I like to bring up something that is kind of hidden in the fine print. Unlike the RTI or TI of a single material, for a system, because you have to use multi-rat tests, and the multi-rats are very expensive to construct. UL do have a provision. If everyone agree, you can select a reference and use the data from the reference, from the known reference, as long as it's no more than 5 years old. Essentially, if you have the same lab doing the test, and the same lab has data from reference system that's no more than 5 years old, and the client agree and UL agree, because it satisfies some of the rule, like no more than 20-degree difference in the thermal class, then you can use those data. And here are the difference between UL 1446, which talk about thermal aging of a system, and SAM 46B, thermal aging of a material. Essentially, UL 1446 is tougher because after each cycle, you have to have temperature shock, mechanical shocks, and humidity conditioning. And the endpoint, instead of using 50% of initial property, they are measuring leakage current, 0.75 amp. That is very high. That means you have a failure. Essentially, they are looking at the failure on the motor rat. And if they see any failure in any of those conditions, winding to ground, between windings, high and low, and turn to turn, it fails. And they would use minimum of 10 motor rats. So that's the thermal aging of using motor rats for major insulation. And obviously, you have recognized that. I mean, if you now it probably would cost 80, 90, or 100,000 for a thermal aging test of major insulation. So, under certain conditions, UL will allow a single or dual temperature thermal aging. So instead of aging it for 5,000 hours or more, it will age it for 1,000 or 2,000 hours. What it is that in order for UL to allow single dual temperature thermal aging, it has to satisfy those conditions. The one that people use most of the time is when they want to reduce the thickness of a major insulation, obviously for cost saving. And instead of going for a full 5,000 hours or more, you can use 1,000 hours. The assumption is that if you satisfy those conditions, your candidate and reference will have a similar slope on the Ahernus curve, and then you just age it for 1,000 hours, and then you go through the mathematical model using the data from the known reference, because you obviously have the Ahernus curve data. And then, okay, you can't do it graphically. You have to do it by mathematics. Dual temperature means you may want to do it at one more temperature, but the second aging temperature will be 2,000 hours, and then you take the average. So obviously, 2,000 hours is a lot better than 5,000 or 6,000 hours. It will be cheaper. The last one, not going to go into too much detail, is a sealed tube test. That's for minor insulation. So again, you have a reference, and you have your candidate. The candidate is would contain the material, the new minor insulation that you want to add to the system, and then the reference is as determined by UL, which will contain most of the material for each class in the insulation system that you want to add the new minor insulation to or substitute for. It is a 2-week test. It will be done in 336 hours. It's a lot cheaper than the than thermal aging. I think right now the price is around $10,000 to $11,000 to $12,000 for UL to do it. Essentially, the theory is based on the fact that if you put all those things in a sealed tube, the outgassing will attack the insulation on the twist wire or the magnet wire, And then what they do is to make sure if your candidate, the degradation of the magnetic wire is no more than half of the reference, then you pass the sealed tube test. Then your candidate material can be added to the insulation system. Okay, lastly, I'm going to talk about the new NEMA LI6 standard. Why do we need this one? We used to have NEMA LI6. The last time it was revised was 2003, but we updated last year, and now we call it IM 60001. And what it does is that it contains actually 47 adherence curves. Those are the essential, the background information that allow the NEMA LI1, now the ANSI NEMA 60000, to publish the RTI number for the material recognized by LI1 or 60000. So those are very valuable historical information, and we want to maintain it. But we realize that we just don't want to rubber stamp it and call it 2022. So what we do is that we add quite a few paragraphs in there to explain some of the misconceptions or pitfalls on the interpretation of the other thermal aging standard from a neutral third-party perspective. And we also recognize that nowadays we need to talk about accelerated RTI or TI methods. So I'm not going to go through that in detail, but then here are some of the examples of what we add to the NEMA IM 60001, because they talk about the pitfall of using a letter thermal class B, class F, class H, because the spacing is too wide. And then when you test the RTI of a material, if it's 170, if you want to give it a letter class, it can only be class F. It cannot go up. But then when you have an appliance, and even though your hot spot is 165, you have to consider it as 180 hot spot. So what that means is that even though your insulation tests out better than the hot spot of the appliance, technically it cannot be used. That's one of them. That's the other one. That's very important, is that this is the first standard to directly state that the RTI or TI of an insulating material, whether it's major or minor, it does not have to be the same or higher than the thermal class of the insulation system. That's very important, because the two tests, even though the concept is similar, it's two different tests. So it doesn't mean that a 155 degrees C material cannot be used on a 180 C system. It is two different things. It needs to be, if the 155 C material is included in the system, 180 C system, it can be used because it was tested that way. It introduced accelerated RTI tests from other parts of the world. The IEC actually call it 60216-7. And JBT 1544, that's the Chinese national standard. They've been around for a long time. Now at least IEC recognize it and call it, a very, very similar one. And IEC call it IEC 60216-7. So what it does is to basically allow manufacturer to get an RTI number without spending $60,000, $80,000 and wait 1 year. Here's my final take. And if you look at a yellow card, or if you look at a manufacturer data sheet and you compare one material to the other, we all do that. And then if you see a 5-degree difference, or in case of yellow card, because the difference will always be 10 degrees C because of the round down, in a way, don't sweat about it, because as I demonstrate, there are so many ways to skin a cat. There are so many different methods. You And also there's a round down of the number. So if you look at a yellow card, it doesn't tell you what method is used. And on top of that, the time period where the RTI was assigned in the past 6 decades could make a difference. For example, if you look at one yellow card, it says that this yellow card was first issued 1986, and it was last revised in 2022. Unlike an engineering drawing, doesn't tell you what the revision was, so you have no idea the RTI number or any number, when was it determined. And one thing I'd like to mention is that like UL follow-up surface, RTI, because it takes so long to do, it's never part of the UL follow-up surface. They would do fingerprinting, they would do frame, sometimes they would do HWI, HAI, short-term property, and that's it. They would never retest your long-term property. So you have no idea how long ago the RTI number came from, on which revision of the standard it was tested against. And also, that's the statistical significance. How good is the correlation, regression correlation on the Venus curve? You don't see it on a yellow card. You don't see it on the data sheet. Last and not, if it's RTI, you have a reference. What's the performance of the control or the reference? If a reference has a certain RTI, but it outperforms, then it make everything look bad, make the candidate look bad. But vice versa, it will make the candidate look good. So, as I said before, just by looking at a number doesn't tell you the whole story. We always have to consider the historical performance of the material in the field. And that's something we always have to remember. Okay, lastly, I've given, I think we cover a lot of ground in the last 45 minutes. Could be very confusing. So if you have any more questions on RTI, TI, or thermal cars, what you can do is to contact us or contact our sales representative. We will be glad to answer any question. And on top of that, if you are not sure whether our material can be used in your UL file or your proprietary UL insulation system, again, talk to us. So, as I said, sometimes it can be as simple as what they call non-testing file update. UL would just look at your presentation and see if they have enough data to give you what you want to do, what you want done, without going through testing. For example, and we have the knowledge, we've done enough of this, we know that there are certain pathways, there are certain workaround that UL will accept. For example, like a conditional recognition, that's something we learned just in the last few years. That if it's good enough after 2,500 hours, then UL will give you conditional recognition. 2,500 hours is 4 months, a lot better than 9 months. And now, this is something I want to bring up also. If TGC would even do a turnkey solution, if you feel that you don't have the resources to handle all this, then UL has a L37 agency agreement. Then we sign that agreement, and we limit the scope of a certain UL file that we work as your agent. We will be responsible for all the testing with UL or UL approved third-party laboratory. We will be responsible for talking to UL on the interpretation of the results. Once the project is completed, then we will no longer be your agent, and we would never have would not be able to see your UL file again. So it is just for the period of the project. And last but not least, I think in the previous slide I mentioned that under commercial agreement, TGC can help or even pay for all the UL courses. I mean, we all know that UL is expensive, but then just talk to us and then we'll work something out. So UL TGC can share costs of UL file update. And at this point, this would be the end of my presentation. Any questions?
Okay. Well, thank you, Solomon. And for those that are here today in attendance, we do have some handouts available for you to download, so don't forget to take a look at that. There's some comparative data sheets there. You can take a look at that, and that allows you to compare properties of different materials. You can also check those out on our website as well. There's frequently we're changing those and updating that. So you can also find some additional comparative data sheets there, and then also find the link in our chat here. So now we're going to begin to answer some questions that were submitted today, and also we had some questions before today that we can start with. But as we're starting with those, don't forget that you can send your questions in through the questions pane, and just send them in on there, and we'll check those and see if we can answer those today. And also you can raise your hand and we will unmute you so you can just ask the question directly. So as we get started here with a couple that we had already people had pre-submitted, you can go ahead and either raise your hand or send those questions in on the questions pane. So let's get started with a question from Robert. Robert's asking, is there a standard for defining polymeric material flexibility or tear crack resistance over time? His concern was about insulating materials that are seeing elevated temperatures over time, and electricians that may remove those and they crack, after a long period of time while they're removing or reinstalling those. So I'm going to try to take a crack at that.
Yeah. Okay. Tear and flex, they are not part of the UL SAM 46B diagnostic test for mechanical. I think for mechanical they use tensile and impact, but there's nothing that stops us from using the methodology of SAM 46B and do the thermal aging against a known reference. Then we know that will perform well as far as cracking or tearing is concerned. So that would be something like testing that the gun company can perform. You just don't get a yellow card for it.
Yeah, exactly. We can just take some side by side. Take some materials, test them side by side, do some thermal aging. There's some ASTMs around tear resistance or tearing, checking the tear properties of the materials. Okay, and let's see here. We're going to check on a question from Noah. He says that at his plant that they run core coil assemblies through a heating process, and that's before they fill it with oil, and that heating process is causing the adhesive in the coils, the diamond craft paper to set. They also draws the moisture out of the coils. It helps improve the paper's electrical properties. Does removing the moisture from the paper improve its long-term thermal performance, or are there offsets that stress from the heating process can cause actually that hurt the properties possibly?
Okay, so that would be a liquid fuel transformer, and most of the liquid fuel insulation systems are 110 and 120C, so we are not that far away from 130C. And then the one thing that with all cellulose product is that the moisture is a bad thing. At elevated temperature, it can cause hydrolysis. It degrades your cellulose and cause partial discharge. So definitely, actually, I think Wyman, when they sell you an insulation package, they advise you to dry it out completely before you fill it with transformer oil. So definitely you have to make sure that the insulation, the cellulose insulation is dry.
Yeah, I would think that the very short period of time that you're drying it is probably not going to be degrading the craft paper. It's probably not too high of a temperature that's going to cause degradation in that shorter period of time. So let's see, we've got a couple more here that we can work off of. Let's see. How about this one? I think you covered this a little bit, but from Kevin, he says, how many test samples are required when doing thermal aging?
You are required at each cycle minimum of 5.
Okay.
For statistics, I think that's like every UL test they do a minimum of 5.
Okay. Okay. Very good. Let's see if we've got anybody raising their hand. Okay, maybe one more from our list of questions from previous. Let's see. How about this one? I think you also covered this a little bit, Solomon, from Chris. How do I know when was the RTI test done when I compare a UL yellow card?
You don't, because that's proprietary information. And as I said before, you know when the yellow card was original issue, for example, 1985, and then it will show you the last revision date, but it doesn't tell you what was revised. And usually, if you have RTI and you like what you see, you don't test it again and again and again, and it's not part of the UL follow-up service.
Okay, all right. Well, I think we have run out of questions here today, and I want to thank Solomon for today's presentation, and thank everyone for attending. We appreciate you being here. If you have any other questions, please feel free to contact us via email or phone. Once you leave today's webinar, you will receive a brief survey to complete. The feedback will help us to further improve our future webinars and the content that we provide you. So we really appreciate that. You will also receive a follow-up email within 48 hours with a link to today's recording. On behalf of the Gun Company and our presenters, thank you for joining us today, and we hope to see you next